Before I start with this epic presentation, I'd like to give you some kind of perspective of what we are doing from space. These are some simulations using a So these are some simulations using a global circulation models. Here in LIMO, it's a European model with physics and biogeochemistry. And these are simulations of the chlorophyll biomass, the annual average from 1998 to 2007. Okay. So on the left, top left here, you have the surface chlorophyll concentration, let's say the chlorophyll concentration within one attenuation depth. All right. Here you have the total chlorophyll concentration vertically integrated from surface to bottom. This is here the ratio of surface to total. And this is the correlation between the surface chlorophyll and the total, right? So you see here, this is basically what the satellite measures. The chlorophyll within the layer for which you have some light. But this is the total vertically integrated. And you see the kind of difference that you have here. For example, this oligotrophic area that we always say, okay, we have oligotrophic areas, the subtropical region, etc. But when you look at the total biomass vertically integrated, you don't have this anymore. And if you look at the ratio here, you see that in most of the ocean, except that is it working anymore? Any more battery? What?
You want to advance the slide or just use the laser from the laser's on the very bottom.
Yes, I know, but it doesn't work. It's probably the battery is gone or something.
Right.
You have another one? You're right.
It must have just got it. So, but it's determined.
Yeah, that way.
This one's okay.
Yeah, that's fine.
All right. Oh my God. Okay. So this is the ratio again of surface chlorophyll to vertically integrated chlorophyll, right? And you see that what you see at the surface is only a very small fraction of the total biomass, like a few percent in many areas, except at high northern latitudes and here and in the coastal regions. Okay. So, and there are many regions of the ocean for which there is no correlation at all between, or very little correlation between what you see at the surface and the total chlorophyll.
Next is the bottom. You say something bottom, so next.
I think it's probably something like 200 meters or something like that. Yes. So I think this is something to have in mind. I mean, there is definitely the satellite cannot tell you everything. You see that you're really missing the vertical dimension. And this suggests that maybe what you should do is to combine satellite observations with in-situ measurements and with model simulations to address some of the important ocean biology and biogeochemistry problems. So this slide is this time the same thing as before, except primary production. So you have like basically surface primary production, total primary production, and the ratio of the two and the correlation between surface and total. So for example, it's just interesting to see these global pictures because, for example, we have sometimes an idea that the polar oceans are very productive, right? Last profit, blah, blah, blah. But if you look on an annual scale, you can see that, in fact, these oceans are not very much productive at all. Simply because you have light only during a certain fraction of the year. But this is important to have in mind, this kind of pictures and variability. And also, it looks like in this case, the prediction at the top is well correlated to the total vertical integrated production, but there are still areas where the correlation is kind of small. So these kind of areas might be difficult if you wish to use the satellite data and infer something about some like geochemical properties of the ocean.
Right. Are these figures coming, are they in a paper?
No, not on paper. I'd like to publish that at some point, but it's not really my usual chemistry, is not really my field of expertise. And what I'd like to do is to be able to understand why we don't have these, why the correlations is so defined.
Well, one point we made with the students in the first week is the fact that the growth field is not necessarily violence.
Yes, well, yeah.
That's all. So yes, it is the ability to catch light, and there's no doubt that when you integrate it with violence also, there's much less differences than compared to the surface. But you just have to be careful.
Yes, well. No, but again, I mean, we have a tendency, I mean, we see all the time these pictures of chlorophyll concentration, the distribution, we identify these oligotrophic regions, and blah, 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 and we seem to understand why. But you see, if you look at the vertical integrated picture, it's quite different. Yeah.
And another point is that in these regions, the biofilms that are there divide every day. So we call them desert, but they're not desert. It's just that there's an extremely tight balance between prey and predator. So it's slow biomass regions, but they're not desert. It's not like they cannot grow. It's not that when you think about a desert, it's a place where there's no plants. There's just no food for them. These cells manage to divide and divide regularly. There's no problem. They almost on a day or day and a half. The whole biomass is replaced. But it's shown, it just gets less than it grows. And it's really tight system. So we have to get disentangled from analogies to terrestrial. Same goes with the blue. The goal of the blue is nothing to do with blue month back. Nothing.
So when you figure that it seems like most of the ocean has the primary ocean, southern ocean, the iron is the same, and the middle and everything. And then some parts that they're all on that side that were higher. So is the paradigm should it be really just most of the ocean is?
Most of the ocean is coupled. And those regions that are mature and where you can get decoupling between fighter and the predator. That's the way I think.
So there's turnover of all the time.
Turnover is always that. More than all year round. I mean, except for polar nights, we need polar. Everywhere else, all year long, pipelines are really good.
Right.
And the ones that are there are the ones that can do the best in those conditions. Intermediates, rapid running.
Okay, let's start with epic. Ocean color remote sensing from the L1 orbit. Do you know what is the L1 orbit? What?
Which is what it is? Stable point, so then put a satellite there, stay there on the other side of the moon.
It's stable in my sense, why is it stable?
It's stable as in this gravitation.
Or without between each two things.
Between the Earth and the system.
There's what's not.
Hence,
We just play the blue sky.
Escape.
It's a sign that you always need the same side of you. That's what it's.
I have the sun.
Okay, so what are Lagrange points? Well, at these points, L1, L2, to L5 here. Let's see this point. Very well. So the gravitational force of the Sun and the Earth, these large masses, equals the centripetal force of a small object that moves between them. That means that the relative position of the three objects are fixed. Right? And if you look at L1 between N1 and N2 here, what you have is basically the Sun always in your back. So you view the Earth as at practically the same scattering angle because the Earth is at 1.5 million miles from the L point. All right, so very far away. So you view this very tiny object, but practically the same scattering angle, and which is, in fact, it's not exactly 180 degrees, but something like 175 degrees. And so from that orbit, you can take images of the Earth. And this is an example here from this EPIC camera, the Earth polychromatic imaging camera on board the Discover Observatory. So basically you have this telescope, you have to take picture of the Earth and some frequency, and this is the kind of picture that you get. And you can see here that you have a blue ocean. All right. Now, what are the advantages of using the L1 orbit for ocean color remote sensing? Well, there are a number of advantages. First, the entire sunlit oceans can be observed simultaneously with high temporal resolution. And this from a single platform. And this allows some detailed coverage of evolving systems and diurnal phenomena. So you can really, again, you see the geometry, you look at the sunlit face of the Earth rotates, so you take different pictures of the same target during the day. Okay, of course, the geometry is different, the viewing geometry is different, but you have we can have multiple observations during the day, which is quite interesting. And I say here that the spatial coverage is not an issue at low and middle latitude, unlike with the polar orbiters. We don't have any problem with sun glint because you may have sun glint one time during the day, but not at the other times during the day. And also you can view better the polar regions, unlike with geostationary satellites. Why? Because you are so far up. If you are very close to the ground, you view at very slanted angles, so this makes your spatial resolution very large. The poles, if you are very far, you can see the poles much better. So basically, you see that you have the possibility to do what multiple geostationary satellites can do in terms of spatial and temporal coverage, and this from a single instrument. Some other advantages are that the radiometric calibration, the stability can be maintained by lunar observations when the Earth has a full moon, which is once a month. That means that you don't need an onboard calibration system. And an onboard calibration system complicates the instrument and it's costly. So you save money and you have something more simple. And finally, the thermal environment is quiet. You don't have any more daylight changes. The particle radiation environment is also quiet. You don't have differences in the magnetic field. You don't need a lot of fuel to maintain position, right? So these are really important advantages, in my opinion. So, and fortunately, we have right now in space a mission, a NASA mission called the Discover mission, with this epic camera. And you can look at the website here to get some details, but just Google Discover epic and get all the information you need. But this instrument provides imagery of the Earth's surface lit by the sun at a cadence of 13 to 22 images per day, optical resolution of 18 kilometers, so it's kind of coarse. We're not talking here like these clearest resolution of 1 kilometer. And you have 10 spectral bands from near UV to near infrared, 317 to 780 millimeter, and with a bandwidth of 0.8 to 3 nanometer. So you can see that you have an instrument from 1.5 million miles that measures with sufficient accuracy, if you wish, in spectral bands, which are very narrow. But the mission has not been designed for ocean colonial sensing, but mostly for ozone and aerosol. However, when you do aerosol, usually the level of signals are similar. than when you do open crop. And so the data can be used to estimate ocean color products like surface solar irradiance, water reflectance, which are the basic variables from which you can derive a bunch of products and do a lot of biology, science. And there's also a band at 687 nanometer, very narrow, which in principle could be used to estimate the fluorescence line height by quantifying the field of the oxygen B band. Oxygen B band is basically the band is centered on this oxygen big band by the inelastic law of the fluorescence signal. Right? You see how it works because of the oxygen absorption. You have in the spectral region or in the spectral band a lot of attenuation by the atmosphere due to oxygen absorption. But because of the fluorescence emission at centers at 685 nanometers, something like this, which is close to the center of that band, we have a feeling of this band by the signal from the chlorophyll fluorescence. So if you are able to look at, if you are able to measure this field, how much the band is filled, you are able to estimate the chlorophyll fluorescence. So this is the technique that is going to be used on future satellites like the FLEX mission. But the problem with using this band on the from this mission here, the EPIC discovery mission, is that the signal-to-noise ratio is limited. But so far, nobody has attempted to do this. Right? Now, some global products for ocean biogeochemistry are being obtained. And they include the surface fluxes above and below surface, planar, scalar, in the UV and visible, also the average cosine for total light, and power, and the water reflectance, chlorophyll concentration. And here I just reminded you the definition of the scalar irradiance, which is an important parameter for primary production, integration over the 4-pi solid angle of the radiance reaching the point in the and the average cosine also is an important parameter to characterize this angular distribution of the underwater water light. And you can see its relation with scalar irradiance. In fact, it's downward net irradiance, that planar irradiance divided by scalar irradiance. And for primary production studies, you want to use the scalar irradiance, but you can see how it is modulated. I mean, how, let's say, how the downwelling irradiance that arrive at the surface is modulated by the average cosine in order to get to the scalar irradiance. So I'm not going to go into any details about how to derive all these products. I just want to show in the next slides some example of these products and how they compare with the typical Moody's products or products that we use usually and derive from orbiting ocean color satellites. So these are examples of daily mean planar power just above the surface of photosynthetically available radiation just above the surface. You have on the left the epic value, global, for a certain date here, with at the bottom the bias uncertainty and the standard deviation uncertainty. And on the top right, you have the corresponding MODIS value, MODIS marker for that day. So here, if you look at the uncertainties, they have been decomposed into bias and standard deviation component. Of course, if you know the bias, you may correct the mark on the top left for the bias. And this could be a product you want to use, but this just to illustrate the kind of uncertainty you have here. So when you compare the MODIS and the EPIC products here, you can see a number of things. First, that the EPIC PAR imagery is less noisy, and there is no gaps at middle and low latitude. And this is due to the fact that EPIC uses multiple observations per day to estimate the daily value. So it describes quite well the dynamic variability of clouds. While in the MODIS product, you estimate the flood on the surface using basically only one observation per day. Right? And in fact, this is why here on the bottom left plot, when you look at the frequency of the data, you see that in fact, the range of the MODIS value is slightly larger than the range of the EPIC values. When you look at the difference between the two products, you see that they are quite consistent. There is maybe a slight bias, a slight difference, if you wish, slightly lower values with the EPIC PAR. And this could be due to the fact that when you observe at the middle of the day, oftentimes you have less clouds, so therefore this kind of tends to have the MODIS products a little bit higher, I would say. And on the right, you have a time series from 2015 to 2022, time series at two locations in the middle latitude and at the equator of the daily PAR. And you have in red MODIS aqua plus MODIS terra average values, and you have in black the EPIC value. And you can really see the usefulness of this data set in some way. First, you can notice that the seasonal variability dominates at the higher latitude, right? Yeah, I think I made a mistake here. It's probably reverse. On the top, it's not the equator that's 50 north, and at the bottom, it's the equator, right? And at 50 north, you have the modulation, the seasonal variability dominates, while at the equator, you can see that the variability is dominated by small scales, small temporal scales. But this kind of results demonstrate the ability of the EPIC instrument to describe really the variability of PAR over a large number of scales with quite good accuracy.
Okay, we need to, is it okay if we break for lunch?
All right. Okay, so we've seen this, one of the products that we can get from EPIC, a daily mean planar power just above the surface. And some of the products are the daily mean planar and scalar fluxes just below the surface. So on the left here, so on the left here, you have this planar power spectral. So daily mean again. So you have that. No, this is the power, and this is the flux at 550 nanometer, 370 nanometer, 340 nanometer, UV to visible. So these are spectral daily mean fluxes. All right, and this is integrated over the spectral range. There is a need for spectral fluxes because, well, the primary production depends on the absorption of phytoplankton that varies quite a lot spectrally. So this could be useful. And here at the bottom, so this is for one particular day, and this is the scalar power just below the surface and the average cosine. Okay. So we put some of the results here that we can get from some interpretation of these curves. Basically, the part below the surface is like 3 to 10% lower than the part above the surface, because the surface are bigger. And the fluxes and the UV, the visible, they resemble integrated flux, of course, but their magnitude depend essentially on the amount of solar radiance that arrives at the top of the atmosphere. There is also modulation by ozone absorption in the UV. And the scalar power below the surface, kind of similar to the one above the surface, or below the surface, the planar ones, but they are larger, as expected. And for the average cosine, we see that the values are quite high, 0.8 to 0.85 in the low and middle latitudes. And this is because the illumination is more vertical, so that means that the average Nadir angle of the upwelling and downwelling process is small, 35 degrees. But the values are quite low at high latitudes, and this is especially in clear sky regions, and this is because the illumination is more slanted and less diffuse. Right. So now, these are products that you can get in terms of, this is the daily mean water reflectance just above the surface, 443 nanometer, using a spectral matching algorithm. Here, the algorithm of Steinmetz, the polymer algorithm was used. And on the left, you have global maps at solstices and eclipses in 2020, so 4 different dates. On the right, you have the corresponding maps from this aqua. And what you can see, again, like for the fluxes is that the spatial coverage is much better with EPIC. Of course, you have more observations because you have more observations during the day. Less, especially at the low and middle latitudes. But the values are kind of similar, so these are very comparable products in terms of values. But in terms of spatial coverage, you can see in the plots on the right here, for these 4 different days, the percent of the total pixels for which there is a retrieval. In red, you have the EPIC and include Bodhisattva pixels that are retrieved. And you can really see the increase, the drastic increase in coverage using EPIC. For example, like on the 19th of March, at the equator, you go from about 15% to something like 50–60%. Quite large increase in coverage. Okay, now so something interesting with EPIC is that you view at the same scattering angle. All right. So you can try to exploit that to do some atmospheric correction, develop some atmospheric correction algorithm. So if I denote by RTO, all right. So if I denote by RTO prime the reflectance at the top of the atmosphere corrected for Rayleigh scattering, etc. As a sum of an aerosol term plus a water signal, water reflectance times atmospheric transmittance. This is kind of proportional to the phase function divided by the cosine of the sun's angle and cosine of the view's angle. So this is a typical formula of the quasi-single scattering approximation. It's a good something good to remember because it basically describes the essential physics, the essential variability with respect to geometry. And plus the water signal, which depends also with transmittance that depends on the C and VC. But for EPIC, the scattering angle is constant here. So you can see that if you plot this residual signal as a function of 1 over cosine SZ cosine VZ, you see that when you extrapolate this coefficient to 0, you will get the water signal. And these are some simulations that shows that for area of continental aerosols, maritime aerosols, some red and blue, different trophic concentrations. So this is 443 nanometer and 551 nanometer. And in this case here, the prescribed chlorophyll is 0.3, 0.03, 0.01, 0.8%. We start with that. Yeah, no, this is the reflectance that corresponds to the viscosity concentrations. And you can see when you plot this term as a function of this predictor here, when you extrapolate to 0, you get something that corresponds really to what is prescribed. So this is the basic of technique that could be used to estimate water reflectance for epic. Now, of course, the methods assumes that the clear atmosphere does not change significantly during the day. So this is kind of a pretty crude assumption. And of course, the relationship is not linear, right? Like this would say in this simplified formula. And that complicates, of course, the regression. But again, this can be linearized if you wish, if you do some, if you look at the signal with respect to a typical signal. Of course, in practice, the atmosphere may be clear during all day. So this, of course, limits the number of key observations and therefore the method's applicability. But again, I think this is by viewing at the same scattering angle and analyzing this kind of simple expression here, you can get some idea about a new method to do atmospheric correction. So this is an application of this multi-directional algorithm to a peak. Here we have the actually I missed a slide, which is remember I was talking about the water reflectance. So this is the surface calorific concentration that you can get here from the OSICO algorithm. So you have the peak again, the modus aqua here, the OC3 type of algorithm was used. There's not that many wavelengths. This epic can be used for calorific concentration. And there is good agreement between epic and modus aqua. We can see these images, and here if you look also at the histogram of the epic and modus, so you see something quite similar, perhaps, except perhaps during this age. Okay, now let's get back to this multi-directional algorithm. So this is the application of this algorithm for one day. So you have the epic at 443 and 551 nanometer. And you can see that in this case, the coverage is much less. I think it is because it's kind of difficult to get all the conditions to be able to apply this method. Like here, just a linear relation between this RT prime and the predictor is assumed. And only epic observations with the predictor less than 3 are used, so that to diminish the impact of nonlinearity, and at least 4 observations are required. There is also a test in the goodness of thinking. So if you have all these conditions, then you have to eliminate many observations. And these are, so this is why you have a small coverage. So in practice, with a peak, this might not be very, in practice, it might not be good way to obtain global maps of water effectiveness. But there is a possibility of a new technique here. And these are some examples for individual pixels of how the method works. So you have this kind of historical observations for each case, and then you extrapolate you will fit and extrapolate to 0, and you get the water effectiveness. But I think, again, even if this is maybe limited for epic, I think the results suggest here a new instrument concept for ocean color remote sensing, which is a conical scanner with the optical axis aligned with the sun. So this allows observations of the same scattering angle, but different views in time. I don't know if you understand that, but let me just okay, again. So, the question is, how do we use the so the question is, okay, from the L1 orbit, we've seen that you can see the kind of a definition you have, you observe the Earth at the same scattering angle. But the question is, can you, and you can exploit that to develop an atmospheric correction that uses the bidirectional information. The question is, how can we do this? Not from the L1 orbit, but from an orbit that is closer to the Earth. Right? So if you remember, the expression of this residual term R aerosols, the reflectance of the aerosol. Right? You can see that if you have the same scattering angle, but you measure a two viewing angle, you can do fine. So you see here that if you measure at two viewing angles, the same scattering angle, if you do R aerosol 1 minus R aerosol 2, and multiply by the cosine, right? You end up with cosine theta v1 p phase function divided by cosine theta cosine theta v1. beside W beside W, and this is equal to 0. You have eliminated your perturbing signal. Right? So this is the principle. Now, how you do this? Right? You eliminate the perturbing signal of the atmosphere, because the remaining signal will be the water signal. You see that? Because the total signal after the typical correction is R aerosol plus RW times. So, and so yes, so you have the signal again. The top of the atmosphere after correction is R aerosol plus the water signal. R aerosol is expressed in this way. So if you do this combination, you have two viewing angles by the same scattering angle. And you can see by doing simply this combination, which is cosine theta V1 times R aerosol 1 minus cosine theta V2 times R aerosol 2, you eliminate the perturbation of the atmosphere. Right? So how can you do this? As I said before, you can use conical scanning. So you can have a conical scanner like that. Satellite moves, like part of the but in order to have the same scattering angle, you need something else. Because the scattering angle that has to be constant. So what you need is to align the optical axis with the sun. In that case, the scattering angle is always the same. So this gives you an idea of a concept that you could think about to do ocean colorimeter sensing in the future by exploiting the bidirectional properties of the signal. All right. So it's so in summary here, I would say that the EPIC Discover mission has demonstrated the feasibility of ocean colorimeter sensing from the L1 orbit. Well, maybe demonstrated is a big word, but I think definitely you can develop basic quantities for ocean biology, biochemistry, like solar radiance, diffuse autoreflectance, and from which you can derive a bunch of things. Here I show chlorophyll concentration, but you can do diffuse radiation coefficient. You can do the fraction of R, so I love phytoplankton. And a major advantage of the L1 orbit compared to this LEO and GEO orbit is the possibility from a single platform to image the entire sunlit ocean frequently. It means to resolve the diurnal variability of biological phenomena. And this is really a major gap that we have in current satellite ocean ground missions. So I think this would really fill this gap quite. And the other advantages are the increased spatial coverage at low latitudes, no sun problem, the better coverage of polar regions and geos, and especially during the summer solstice, and no need for onboard calibration system. So so the thing is that the spatial resolution of EPIC is 18 kilometers in a year. And of course, this is quite coarse for ocean colonial sensing applications, especially in coastal region. There's desirable spatial resolution is 1 kilometer or less. So to look at the resolving power, the angular resolution of an optical system, it's 1.22 times the wavelength divided by the distance, the diameter of the lens aperture, right? So typically from at the Earthwine point, if you have a diameter of 0.5 meter for the primary lens, you can get 1 kilometer spatial resolution at 500 millimeters. But this would require a large telescope, a huge antenna. The EPIC antenna is 30 centimeters, so now something much bigger. But you can envision several instrument concepts like a full disk imager, which is the same as EPIC, and also use a CCD and you take pictures. But you need this time aggregated CTVs because the spatial resolution is much better. The aggregated CTV with color planes, but you can also think about some geographic scanning instruments. But there are some issues, of course, because you are quite far away. So image stabilization to compensate for the spectral jitter is an issue. Correction of square light, if you have this kind of system in particular. And the big issue is the cost of the telescope and of placing a large instrument so far away. So these are the issues, but if you look at preliminary calculations and considerations and heritage design, you see that it's feasible really with an hyperspectral polarimetric sensor measuring from UV to near-infrared with 1 kilometer resolution for L1. Right? And I think really the Space Agency should consider such a mission from the L1 orbit and start do some pre-phase study, things like that. So this is something quite different from what we've been used to. Aircraft, the assets we've been using, aircraft, satellite, polar orbits, geostationary satellites. This is another possibility, but you can see the advantages if we can build an instrument with the proper spectral resolution and the proper spatial resolution, which is feasible. So I would really encourage those who are interested in ocean growing or something here to look into this data and maybe see what can be done, explore this kind of ideas. Right, any questions? Looks like being on the face.
In terms of cost,